this one right here is equal to big G mass 1 mass 2 over r squared, where r is that distance. And then it is pointing towards the center of 2. Matter of fact, no matter where 1 is, it's always pointing, that force is always towards the center of 2. So negative r hat 2. So the force on 1 is towards the center of r2.
So when r hat is pointing away from the vector, it's positive, or sorry, the center, it's positive, and
Yes.
when it's pointing towards the center, it's negative?
Yes.
And it's the other center of the thing it's going towards,
Yes.
and that's its own center. Okay.
Why is it R subscript 2 instead of R subscript 1?
Because we're looking at the force on mass 1. So the force on mass 1 is pointing towards 2.
So,
It is pointing away from 1 here, but it's always, no matter where I am, it's always pointing towards the center of 2.
so can I ask a question then? When you say away from the center on the board, are you talking about its own center or the other center? Because then how is r hat positive?
In the case of force due to gravity, it's an attractive force, it's always positive. A centripetal force is always, rewind. Gravitational force is an attractive force, it's always going to be a negative r hat of the other mass. Centripetal acceleration is always towards the center of whatever the circle you're going. And didn't think I'd use it again, but centrifugal force is always away from the center. You generally see the positive r hat is if I'm identifying, if I have some object and I'm doing everything based upon the center here.
Mm-hmm.
So I'm not doing rectangular coordinates where I can figure out how far over, how far up. I'm going to figure out how far away am I. So if that's a 30-degree angle and 5 meters, then I would express that vector as 5 meters r hat plus 30 degrees theta hat.
Can I come up to the board?
Sure.
So you say away. I'm imagining the tuning away from this center, but this is going towards it, and it's positive r?
Look, I got the negatives.
Oh, it didn't. My bad.
Yeah, traditionally you put the minus sign in front, even though it's related to the direction.
Thank you.
Yep. The main thing is to remember gravitational force is attractive, so it's going to be pointing towards the other object.
Could you do minus R hat, so instead of putting the negative in front?
If you're going to do that, you would then write it as big G mass 1 mass 2 over r squared negative r hat. You need to have the parentheses. I've had too many students drop the parentheses and it looks like they're doing a subtraction problem.
Why is r hat negative in this situation?
What is the direction of the force on 1?
Towards the other?
Yeah, towards the center of the other one.
Oh, so it's towards the center of the, okay, just because on the drawing it looks like the forces are away from the center because the arrows are pointing towards not the center of each one. Does that make sense?
Yeah, so you're saying it's away from the center of 1? And away
Yeah,
from
so like
center
the
of
arrow
2?
that's on 1 is away from the center of 1, so that makes it seem like the r hat would be positive. So it's in respect to the force that's the mass.
If you're
that's-
doing it away from the center of 1. So let's look at it, and I think this addresses this, I think I've had 3 variations of the same question. If 1 is over here, I know the direction of the force acting on 1 would be that way. If all I said was it's away from the center of 1, that doesn't really tell you anything because if this is -1, that could be in that direction, that direction, that direction, that direction. It is incredibly vague.
But if it's relative to the other, then that's why. But if it's relative to the other mass, then it tells you exactly which direction it is.
Yeah, if I know where the other mass is, then I know exactly where the direction.
Okay. And that's the reason that they do it that way?
Yeah.
Or is that just a random?
No, I would say that's the reason why they do it that way.
On a test, will you give us the big G?
Yes, I would give you, that would probably be the very first thing where I generally put the constants, or pseudo constants. Now, a couple of notes on the universal gravitational constant. As we as humans observe how far other galaxies are moving, they're not moving the way we expect. So there seems to be some issue with our understanding of gravitational forces. There are all sorts of explanations for it. One of the explanations was that this value is not universal, which is one of the reasons why universal doesn't really get written anymore. There also, out of this comes this idea of dark energy and dark matter. And there definitely, I've seen evidence of dark matter existing, dark energy I'm still a little fuzzy on. So that's another, that there's masses out there. Perhaps this is universal, perhaps it's not, we just don't know. There's also no comment on whether this is constant with respect to time. As in, was this the value 6 billion years ago? Don't know. There are some who have made justifications for it having changed over time. But there are people who are trying to, I think there was someone who was shooting for the universe being only 4,000 years old. Or no, 6,000 years old.
The entire universe?
The entire universe 6,000 years old because of the Bible. And played around with the numbers till it worked for him.
If you have to adjust the numbers to get your solutions, probably not.
Yeah, it definitely violates Occam's razor.
Okay, so you kind of, in my mind, I'm not sure why you did this, but you spontaneously added r hat to the f sub g formula. Should I put that with the general equation, just in case?
Oh. This versus this?
Yeah.
This is the magnitude. There's no vector symbols anywhere on here. This is the more formal definition. Typically, you're going to define the magnitude and you're going to think through what the direction is. Let's run an example. I have a 1 times 10 to the 5th kilogram mass. I have a 1 times 10 to the 6th kilogram mass. They are 0.1 meters apart. What is the force acting on? We'll call this mass A and mass B. What is the gravitational force on B from A? So plug a jug. I know that the magnitude is 6.67 times 10 to the negative 11th times 100,000 times a million divided by the distance squared. And you end up with 667 newtons. That's the magnitude. I picked numbers I could do in my head. But the question is asking for the vector force, not the magnitude of the force, and it is pointing that way. I know it is pointing that way. And so it would be, I could write it as negative 667 newtons R, so A hat. Or given the setup, I could say, well, to the left is negative, and just get along with, treat it as a one-dimensional problem. And then if I do that, negative 667 newtons. Questions before I change it slightly?
Just wait for a hot second, I'm still writing down what was on there. What's that arrow underneath the negative 667N? Is that just,
That if I treat this as a one-dimensional problem and define to the left as negative.
oh, okay.
So if I do that, then I can write my answer as negative 667 newtons.
So even though it's pointing to the left, you still have to.
Pardon?
Even though it's pointing to the left, you still have to.
Yes, yeah. This is defining my coordinate system right here, and then my answer is indicating it is indeed in that direction. Now I'm going to give you a problem that has really messed up some students, though it shouldn't.
Alright, let's go.
So it comes down, and this is especially true in 152. You think through the directions and find the magnitudes, or play very strict adherence to the math. Trouble comes in when people start mixing and matching. So I have my 10 to the 5th kilogram mass here. I have my 10 to the 6th kilogram mass there, a distance of 0.1 meters apart. A, B, and C. And then I have a 10 to the 5th kilogram mass over here. That is also 0.1 meters.
Could you go back to the last screen for a hot second? Okay, thanks.
What is the force on B?
What is the force on
I know we got a 667 Newton force here. This is just symmetrical, so I've got 667 Newton force over here. What is the total force?
Is it not just zero?
It is indeed just zero.
I thought this was gonna be hard.
No, I said it's messed up students, but it shouldn't have.
Damn.
So, here's the proper way of doing it. Here's the thinking through the directions. You do the math, you come up with 667. I know that 667 newtons this way, 667 newtons that way. Two forces, opposite directions, they cancel each other out, total force is zero.
My thought process was just kind of like, if you add the forces from A and C, and then you would realize that one of them is negative, and then it would cancel out that way.
It's the students who don't realize that it's negative. That they would see, oh, I got 667 here, I got 667 there. I just add them up and I get 13, whatever. Now, here's how you could do it, paying partial attention to the mathematics. So this force right here, so the force on B would be the force on B coming from A. Should be a little subscript G. Plus the force of gravity on B coming from C. So total force is the force, sum of the two forces. So negative 667 r hat minus 667 r hat. So this is paying partial attention to the math. You plug it into the formal equation and you look at that and you go, oh, it's negative 13 whatever r hat. The trouble is, those are not the same r hats. This is A and that is C. They are pointing in different directions. What you would have to do is recognize that at this point, I know r A hat is going that way, r C hat is going that way, away from A and away from C, and that they are negatives of each other, so this would be negative 667 r A hat minus negative 667 r A hat. Since RC is the negative RA at this point. Just be aware. This is one of those questions that I've thrown into, I remember throwing it into a multiple choice thinking, okay, here's an easy one. And the number of students who missed out on easy points. Now, I do want to get to a question Stephanie had asked earlier about can you use this instead of NG? Yes, but let's.
I didn't even remember asking that.
Thanks, Stephanie.
But I would love to learn now that you have mentioned it again.
Even I.
All right.
Is that her?
Oh, it is.
Or you, in your own drawing, make that person anyone you want. I want to figure out the gravitational pull between these two people. I know that the force due to gravity, let's look at the magnitude, is equal to mg, because I'm right there at the surface. That should also be equal to g mass 1 mass 2 over r. This is the mass, I guess I have to figure out which one's mass 1, mass 2. What do we call this? Mass m and mass e. This is mass m, this is the mass of me. That cancels out. So little g should be equal to big G times the mass of the Earth over, that should be r squared, the radius. What distance is it? If I'm standing on the Earth, what is the distance?
From where? The core?
Well, that's the question. What is r? Is it surface to surface?
It's surface to core.
In this context, you can get away with that, but more generally, were you about to say something? So surface, you said surface to core, surface of what?
Surface of the Earth, like the lithosphere,
So surface of the Earth to the core of,
the Earth.
if I want to find the gravitational force between me and the Earth, I have two objects. One of them's got to involve me, and one of them has to involve the Earth.
Were you not asking the radius of the Earth?
I was asking for what is r.
Oh,
Distance from me to the center of the planet.
So which part?
Center of me.
Yeah, it's from center to center, center of mass to center of mass. Now, in this particular case, in this instance, since I'm right near the center of the Earth, or right near the surface of the Earth, the distance from my core to the center of the Earth and the distance from the surface to the center of the Earth is practically the same thing. Getting, I think, to what Robin was going for. So 6.67 times 10 to the negative 11 times mass of the Earth, 5.98 times 10 to the 24th. Radius of the Earth, 6.38 times 10 to the 6th squared. And you get
9.8.
would hope so.
Yeah.
Did you actually calculate that, or you just, okay. If you actually calculate it, what do you get?
Is that 10 to the 6 on the bottom?
Yes.
So would that be in, what would be the units for that?
What would you guess?
I got 9.799.
Which is 9.8.
Somewhere there. Units?
M over S squared.
We better get the same units as acceleration.
I fear what may happen should we not. Could you go to back to the last slide? I didn't quite finish writing it down.
But notice from that formula that we had up there that we can figure out the mass of the Earth. If we can figure out the radius of the Earth, which was first done pretty darn close, 3,000 years ago, finding the radius of the Earth. And so there is a mechanism for figuring that out. Big G is a constant, which we've known since the late 1700s. And what we're left with is, we know the acceleration due to gravity. What we're left with is mass of the Earth. We can solve the mass of the Earth that way. There are other ways. Yes?
So in this context, would f of g be equal to little g?
F sub G would equal mg. So going back, the mass of, the little mass was canceled out. So that's how we got down to just plain old G.
Because it's pretty much inconsequential.
Yeah, acceleration due to gravity does not depend upon the smaller mass.
Okay, could you go back?
So therefore, is like, in a problem like that, kind of just solving for the acceleration?